All right, so today we are taking a look at section 5.1 in our textbook. And we are going to be taking a look at angles. All right, so we're going to start kind of fundamental with our angle notation, but then we're going to be moving very quickly from the idea of just an angle to like what angles in a circle look like. Okay, now this circle, if you have taken trig before, you have heard about this unit circle. It tends to be a very not great thing for most students. I think that we see it as like this whole big thing that we just have to memorize. And the bad news is you do have to memorize it. Like, I'm not going to beat around the bush there. It is something that is 100% worth memorizing, but the process to get there takes some time. Okay. But before we get into that, let's kind of start with just drawing some pictures. Okay, so we're going to be drawing some angles in standard position based on this definition. All right, so an angle is the union of two rays with a common endpoint. All right, so they have a common endpoint, and the endpoint is something that we call the vertex of the angle, and the two rays make the two sides of the angle. All right, so if we were to think about how to draw an angle, maybe we could say, all right, here is a common endpoint or a vertex. And if I drew an angle that was like this, and this was my angle, I could also label some of the other parts that the vertex is the pointy part of the angle, and we have two rays. What word would you use to describe the size of this angle? And you can go ahead and unmute yourself, or you can just type something into the chat. There's a ton of different ways to contribute in this class. You can type it into the whole chat. You can type a message just to me. Anything is fine. Cool. So we are in agreement that this is an acute angle, right? It is one that is specifically smaller than 90 degrees. If I were to draw one that was kind of like this, and no matter how questionable my drawing is, as soon as I put that little square in the corner, Jesus is correct, we end up with a right angle here. All right, and then last but not least, maybe I have something like this. And I have this angle here, and we would call that one, exactly, Casey, we would call that obtuse. Okay, so we've got, a little bit of that background knowledge. We've got some acute angles, some right angles, some obtuse angles, and we're going to be spending a lot of our time really with acute and right angles, but also thinking about how we're going to take obtuse angles and maybe give them a different name. Okay, so some basic terminology. All right, so much of this course is really about the vocabulary, and I know that that can be such a sort of scary thing to embrace, but at the same time, we're really thinking about being able to speak like mathematicians in a way that's really clear to any person that we might speak to about the stuff that we're learning. Okay, and so we're going to start right here. We're going to call this, I'm going to draw a ray that is right along the positive x-axis. And that we're going to call the initial side. Okay, so the initial side of the angle is along positive x-axis. Right. Now, if we have an initial side, we actually also need something called a terminal side. All right, terminal side meaning it is the end of the angle. And so if I wanted to draw an obtuse angle, maybe I put the terminal side right here. All right. And then two things I want us to notice about this. I would say that we've actually created two angles here. One of them is sort of this part right here, right? That's an angle, that's an obtuse angle. But the other one, it might be like, well, what if we go the other way to get from the pink to the purple? And so we're going to label these differently, okay? In this direction. So the arrowhead there is actually really important. When we are going counterclockwise, all right? So counterclockwise, we are going to, anytime we count in that direction, it's going to be a positive angle, all right? On the flip side, literally on the flip side, if I count in the other direction, okay, so now I'm counting clockwise, I'm not going to get a positive angle, but I'm going to get a negative angle. All right, and so we're going to see that in a little bit, but the positive and negative part is really just about which direction you are counting in. All right, and so in particular, positive means we're starting at that positive x-axis and going around. It's the same direction that we count the quadrants in. So if you recall from maybe previous math classes, we have quadrant 1 over here, quadrant 2, quadrant 3, and oops, didn't leave myself enough room. We'll go quadrant 4 over here. Okay, so the direction that we count our quadrants in is the same direction that we call positive angles. And if we go in the opposite direction, we're just going to get negative angles. Okay. All right, so there are some special angles here. All right, and in particular, if we started at our initial side right here, and we counted until we got to, let's do this thoughtfully. Let's say we counted until we got to here. All right, the highlighted purple. How big is that angle? It's 90 degrees, right? 90 degrees if I count this way. All right. So let's say that we keep going and we go from, those are not significantly different colors. We get all the way to here. If we go from the pink to this other purple, how large is that angle? 180. Nice, I agree. And if we go all the way around, almost, and we get all the way down to here. So we start at the pink, we go all the way to here. How many degrees is that? All right, so we've got a 270 here. Now, what if we were at the pink line and we just stayed there? How big is that angle?
360 or 0?
So if we stayed there, it's zero. But if we went all the way around, we would get back to 360. Okay, so you can think about it as 0 or 360. Now, these are all the positive angles, but let's practice counting in the other direction. Okay, so we'll go in the negative direction. If this right here is 0 and I go this way, instead of calling this 270, what else could I call it? Good. I could call this negative 90, right? Because all I'm doing is counting 90 degrees, but in the other direction. Okay. So if I continue, I start at the pink, I go in the negative direction and I get here. How big is that angle? Or what's another name for 180 degrees? Yeah, we could say negative 180. I agree. All right. What's another name for 90 degrees? Sure is negative 270. Okay. And so you'll notice that like we could call something 90 degrees or we could call it negative 270 degrees, but they're the same angle. Okay. So one thing that we're going to find is that a lot of our angles have nicknames, right? So maybe it's 90 degrees, but maybe they want to be called negative 270 in a particular problem, right? Or maybe our angle is 180 degrees, but for the particular problem, we want to call it negative 180. Or maybe we're right here and we want to call that 0, but sometimes we want to call it 360. Okay, so we have to be really thoughtful about how we're naming these angles. But the ones that we've highlighted here, the ones that sort of divide up the quadrants, these are called quadrantal angles. All right. The quadrantal angles are the ones that divide the quadrants. And these are really sort of quote unquote nice numbers for us to know. 90 or negative 270, 180 or negative 180, 270 or negative 90, and 0 or 360. Okay. All right. So it would be a disservice to sort of hide this unit circle from you and sort of pretend like, oh, at some point, like, you know, maybe you'll need to know it. I like to put this out there the very first day and just kind of dive right in, okay? But using what we know about angles and degrees in particular, we're going to fill out all these angle measures. Now, anyone who's seen trig before has a little bit of a heads up, but before we even start filling these things in, can folks sort of in the chat type in like, what are some nice angles? All right, nice being in quotations. Nice really means that these are ones that we tend to see a lot. What are some nice angles that we know? We've listed a few, like 0, 90, 180, 270. Great. All right, 45, 30 degrees, 60 degrees. All right. Anyone else think of any other sort of nice angles that we have seen in our mathematical experience? All right. So based on what we were doing just before, this is essentially where our pink line is, right? Ooh, I like that 300, 350, or 315, 330. Yep, those are some other great ones, right? And so now the question is, where do all of them go? I love it. 120, that's also a super common one. Okay. But if we start here, and I'm going to ask that we put our degree measures in the oval-y shapes. Okay, so 0 degrees. We know this one. We know that's 90 degrees. Before we fill in all the rest of them, what do we think this one is? Yeah, 45, right? Because I have this 90-degree angle, and then I sort of cut it in half. You sort of have to like squint your eyes a little bit, maybe blur out the other lines that are there. But what we have with this one that I've just drawn down the middle is it's literally in the middle. And so half of 90 is 45 degrees. Okay. All right. Well, if I know this is 180 degrees, what's this one? The one that is halfway between 90 and 180. All right. So I add 45 to 0, I get 45. I add another 45, I get 90. I add another 45, I get 135. I add another 45, I get 180. So if you add 45 one more time, it should get you to here. All right, so let's do a little bit of that mental math. 180 plus 45 should give us 225. I love it. All right. What did we say this one was down here? The one that points straight down. 270, great. All right. And if I do 225 plus 45, I'll get 270. Okay. I'm going to add another 45 degrees to get me to here, 315. And if I add another 45, I will get to 360, which is the same as 0. Okay. So one thing that you'll notice is I didn't go through and just label every single angle along the way. That is one way to do it, okay? But if you're feeling nervous about this idea of memorizing all of this, one of the things that I found super, super helpful is that we look for patterns, okay? So one pattern is that we can add 45 and keep getting all of these pieces, all right? Now, I think Dallas mentioned some other sort of nice values, and in particular, one of them was 30 degrees, right? And no matter how much you love or hate angles in trigonometry, if you know that this angle is 45, how big do you think this angle is? Give me a good guess. Yeah, it's probably going to be 30, right? It is a little bit closer to 45 than it is to 0, right? It's a little bit closer. And so that turns out to be our 30 degrees. So if you can add by 45, you can get all the ones we've already filled in. But if you can add by 30, you can fill out everything else. All right. So let's take a look. We've got 0, 30. So this one will be 60. Good. And what's 60 plus 30? 90. Great. So we have our 90-degree angle. We cut it into 3 equal pieces, and we got 0, 30, 60, 90. Okay. Great. Let's keep adding 30. All right. So what do we get here?
120.
120. Great. We got 135. What comes after 135? 150. Good. And 150 plus 30 gives me 180. Great. All right. What's the one between 180 and 225? Great. I add 30. Okay. Let's add 30 to 210. We'll get 240. We add 30 to that. We get 270. We keep adding 30. And I think now we've achieved some of those values that Avi had put into the chat earlier, right? 300, 315, 330, some of those bigger angles. All right. So degrees in our unit circle, right? We're so used to working with degrees that this tends to make a lot of sense. I have a little bit of bad news. And that bad news is we're going to use degrees, but not really that much. In fact, we are going to use a measure called radians. So if you know your degree measures, great. It's also going to be incredibly important that you know your radian measures. Okay. And so that's why I wanted to show us like sort of a pattern we could follow to fill in the unit circle with degrees, because we can actually use that same pattern to help us fill out with radians. Okay. All right. So what is a radian? Okay. A radian is nothing more than another way to measure an angle or to measure angles. Okay. So it's another way to measure angles. It's almost like if you wanted to measure how tall you are, right? So usually if you live in the States, we give our height as like feet and inches, right? So height usually is in feet and inches. How many inches are in a foot? Yeah. But if you are either from other parts of the world or travel frequently to other parts of the world, you might notice that they don't really use this imperial system, but they use the metric system, right? And so more typically, people not from the US will give their height in like centimeters or meters. But whether you're measuring your height in feet or inches, or you're measuring them in centimeters or meters, you're still measuring your height, right? So if someone says feet and inches, that's great. There's a relationship that you can do to actually convert that to centimeters or meters, right? But they're still describing your height, okay? So as scary as the idea of a radian sounds, it is nothing more than another way to measure angles, okay? It's another way to measure angles. All right, so how do we describe this? So the radian is about this big. This is about 1 radian. Anyone want to give a guess as to about how many degrees that's equal to? All right, we get a 30, maybe a 60. Okay. Yeah, it doesn't quite look like 45 to me. It looks like one of the other ones. Now, maybe if we sort of like draw in this, right? So how many degrees did I just draw right now? Like the whole red line? 180. Okay, so now let's think about maybe a guess for that radian measure. What do we think? We've got 2 guesses out here, about 30 or about 60. Do we want to revise our answers? Or maybe we have more information about that. Okay, so I see another guess for 60, right? And so 60 is like if I take 180 and I cut it into 3 pieces, that kind of actually looks like it fits, right? Maybe 45, right? So how would we know if it's 45 and we drew it like this? This is a 90-degree angle. 45 would have to cut it exactly in half, right? So to me, this looks more like it's a little bit bigger than 45 degrees because it's like bigger than half, because half of this angle might be like something like this, right? So one estimate is a radian is approximately 60-ish degrees. Okay, so a 1 radian is approximately 60-ish degrees. So you folks tell me, which one is bigger, a radian or a degree?
Radian.
Yeah, a radian is bigger because how many degrees do we have in a whole circle? Yeah, we have 360. How many radians do you suppose we have in a whole circle? Yeah, we have about 6 of them, right? And if we wanted to be as precise as Dallas, 6.28-ish, right, is actually the precise number. But let's kind of draw this out, okay? So let's suppose that we have a radius of, let's say, 4. And this is also the radius, so that's about 4. And this piece right here is also the radius, which means that piece is 4, okay? And if I wanted to draw another slice kind of like it, this would be maybe another one, and then maybe like one like here, that would be the third one. Third one, fourth one, fifth one. And actually the 6th one, if we did it super, super accurately, would only get us almost all the way around. Okay. So if I wanted 6 radians, that would measure out something that would be like this, but it wouldn't be the whole circle. Okay. So there's like a little bit left over. So it turns out that there are exactly 2 pi radians in a circle. All right, there are exactly 2 pi radians in a circle. Now, I think that pi is a familiar number to us, and sometimes it's so familiar, we might actually forget that it's a number, but it is. And so if we were to estimate pi, it is about 3.14159-ish, right? It kind of keeps going forever and ever. So then 2 times pi would be 2 times 3.14159-ish. And if you multiply that out, right, if you have a calculator or you have Desmos handy, you should get about 6.28-ish, right? So that means that in a circle, there are 6.28, that's that little piece right there, radians. There's not 360 of them. There's 6.28 or 2 pi radians in one circle. Okay. It's a different way of measuring an angle. That is literally it. So it's like the meters to our feet or the centimeters to our inches. Okay, it's just another way of measuring things. So let's talk about converting between degrees and radians, because it is a pretty valuable skill for us to think about how we convert between things, okay? So converting between degrees and radians, right? What we know, all right? We know sort of more or less what a degree looks like. And in fact, if I start with my initial side on the positive x-axis, I know that this is 0 degrees. I know this is 90 degrees. So if I wanted to draw something that was only 1 degree, maybe it would look something like this. In fact, it would probably be even smaller than this, right? But this is about 1 degree. And if I wanted to think about radians, like that picture that we just saw, if we start at the initial side on that positive x-axis, this would be 0 radians. And we usually abbreviate that rad, okay? How many radians is it when I get back to here? Yeah. So we have 0 or we have 2 pi. Well, if this is 0, and when we get all the way back around, we get to 2 pi, what do you think the measure of this angle is? I see a pi. What do other folks think? How big might that angle be? Okay. And what's our reasoning? Like, how are we getting pi?
I think of it as if it's like almost as if pi is like its own thing. If you take 2 of them, just half of 2 is 1.
Yeah, exactly. Great. I see Jesus saying the same thing, right? So we have this whole thing is 2 pi, which I know is sort of weird for us because, you know, when we think about like an actual edible pie, like it's usually the whole thing, right? But this is 2 pi for us mathematicians. That means that if I take only part of it, in particular half of it, half of 2 pi will give me 1 pi. Right? What does that make this angle then? Yeah, I've got pi, but now I only want half of it. So this is pi over 2. So I've got 0, pi over 2, pi. How big is this bottom angle going to be? Okay. Another way to ask that same question might be, what's halfway between 1 pi and 2 pi? Or what's halfway between 1 and 2, right? Halfway between 1 and 2 is 1.5, right? But we don't want to say 1.5 pi, so we call it 3 pi over 2, right? 3 halves being the same thing as 1.5. So down here, we can say 3 pi over 2. Right? But all of this is to say there's a relationship that we can convert back and forth between degrees and radians. And so one true statement that we could write is that 360 degrees equals how many radians?
2 pi radians.
Yeah, 2 pi radians. All right, so 360 degrees equals 2 pi radians. Okay, well, what does that make pi radians then? What is that equal to in degrees? Yeah, that's going to be 180 degrees, right? And so from this relationship, all right, you've probably seen a number of things in textbooks or other classes, but it turns out that we can use the idea of ratios to help us convert between units. All right, so what I mean by that is we can say that if we have an angle and we're measuring it in degrees, okay? Let me just draw that symbol again. This symbol is called theta. I'll write that off to the side. So this is like an O with a horizontal line in it. We read this as theta. And it's just our grown-up way of saying an angle, okay? And so when I write theta, when I write theta with the degree symbol, like I did down here, I mean, I have some angle and I'm measuring it in degrees. And if I put that over 180 degrees, that would be like my degree ratio, but that should be equal to the degree in radians over pi. Okay. Now, a lot of times we write our degree symbols. We have a little like circle O in that subscript or the superscript. But when we're talking about radians, a lot of times it's actually implied. So we don't even write radians. Sometimes we write rad, and sometimes we don't write anything at all. And so it's almost incredibly important for us to write the degree symbol, because if we don't write the degree symbol, other people may think that it's actually in radians. Okay. And so we have this proportion that takes care of our degrees and our radians. All right. And so as long as you fill in the right numbers in the right places, then you can use this one formula for all conversions. All right, so let's actually take a let's do some examples and then we will then we'll take a little break. Okay, so let's take a look at drawing some diagrams, figuring out angle measures in degrees and angle measures in radians. Okay. This is a very, I would say, like very classic Judy kind of diagram, in the sense that I like us to know how to draw pictures. All right. So if you're new to the class, you're going to find out you're going to be drawing a lot of pictures. But I also like you to know how the picture helps you think about a visual for the degrees as well as a visual for radians. Okay. And so we're gonna, in one case, I've given you the measure in radians, the other I've given you a picture, the last one I gave you a degree one, and oh, look, it's a negative one, right? So all these different pieces, I want us to make sure that we know how to convert between. And so let's start with this first one right here, all right? So we've got an angle measure in radians, we've got pi over 9. And so the first thing I'm gonna ask us to do is actually convert this to degrees. And so all we're going to do is we're going to go back up into our notes. We're going to grab this formula right here. Pi or theta degrees over 180 degrees equals theta over pi. Right? So we've got theta in degrees over 180 in degrees equals theta over pi. And everything on that right-hand side is in radians. And now the only piece of information I have is pi over 9. Where should I put that pi over 9? Does it go in the left numerator or the right numerator? Yeah, and what makes you say that, Dallas? Why would we put this on the right numerator? You're correct.
Because it doesn't have the degree sign.
Exactly, right? If this were measured in degrees, then I would put it on the left-hand side. But it's measured in not in degrees, exactly. It's measured in radians. So I'm going to put that on the right-hand side. All right, so we get theta degrees over 180 degrees equals pi over 9 all over pi. Okay. I know that sometimes fractions, and especially fractions with pi, make us nervous. This is why I'm writing this right here, because I want us to embrace the nerves and just say, this is going to be part of the course. We're going to be okay with this. I earned my spot in this class. I can handle this kind of math. Okay. So how do we handle this? Pi degrees, or sorry, theta degrees over 180 degrees equals, another way I can write this is pi over 9 times, if I'm dividing by pi, I could also multiply by the reciprocal. right? If we think back to fractions, I can just multiply by the reciprocal. Now, what about this form makes my life a little easier?
You can cancel out the pi.
Perfect. Now it's a little bit easier for someone to see, oh, those reduce and they go to 1. And now we're starting to look like it's a lot less scary. So we get theta degrees over 180 degrees equals 1/9. Great. And what is my last step to get theta degrees by itself? Yeah, if I multiply both sides by 180, I get 180 degrees times 1/9. And turns out that pi over 9 is a fancy way of saying 20 degrees. All right. So one formula, plug in whatever information you have, and then solve for the thing that you're looking for. All right. Now, if we want to finish up this example and draw a diagram, all right, I want to think again about my initial side. Whoops, my initial side here. And then I want a 20-degree angle. Whoops. So maybe somewhere like kind of like here is my terminal side. And this we just want to label as theta equals 20 degrees or pi over 9. All right. All right, any questions on this first example here? Great. Well, I'm going to go ahead and pause the recording for a moment. All right. So before break, we took a look at one example where we were given an angle measure in radians. We converted it to degrees and we drew a picture. Okay. So now we have one where we have a diagram, and I'd like us to fill in the rest of that information. And so if we take a look at this diagram, I bet we can answer one of these two questions pretty quickly, right? From our diagram, what information do we have that we want? Yeah, exactly. We have 160 degrees, right? We have the degree measure. And so it is literally just writing 160 degrees in the degree box. That is it. Okay. So then the work really here is in finding the angle measure in radians, right? So let's go ahead and grab that same formula we used earlier. So we've got theta degrees over 180 degrees equals theta radians over pi radians. Last time, we took this pi over 9 and we put it in for the theta on the right-hand side. This time, though, we have 160 degrees. So that means we should fill in the theta degrees or the theta on the left-hand side. Okay. And so when I plug that in, I'll get 160 degrees over 180 degrees equals theta over pi. Right. All right, I'm going to challenge us to do a little bit of mental math here without a calculator. I'd like you to go ahead and reduce 160 over 180 to the most reduced fraction. All right. So where might we want to start in terms of reducing that fraction? Yeah, we can reduce those zeros away, right? And a fancy way of saying that is we're actually dividing by 10. And so we'll get 16 degrees over 18 degrees, which makes, I think, our lives a little bit easier now. We could probably reduce one more time, I think. Yeah, we'll get divide by 2, we'll get 8/9. Great. Okay, so we've got 8/9, and we know that that equals to theta over pi. And so if I want to get the theta by itself, what do I need to do? Yeah, we're just going to multiply both sides by pi. And it turns out that what else reduces is the degrees. Those units also reduce. Okay, so we end up with, let's actually put this in the next line. We get theta equals 8/9 times pi. That's one way of writing it. I tend to write it with the pi in the numerator, so I will typically write it 8pi/9. Okay, but they are mathematically equivalent. 8/9 pi or 8pi/9 are the same thing. Okay, and so there we have our angle measure in radians. So it turns out that 160 degrees is equivalent to 8pi/9 radians. Okay. Which makes sense because this is almost 180 degrees, but not quite. And this is almost 1 pi, but not quite. All right. All right, so we've got one last one. I wanted to throw a negative angle in there because I think, again, it's important for us to just embrace the reality that we're going to deal with negative angles. Okay, and so from here, let's go ahead and find the diagram first, so we can sort of get a visual of what we're even trying to convert. All right, so we have this as our coordinate axes. We've got our initial side. And just as a reminder, we've got quadrant 1, quadrant 2, quadrant 3, quadrant 4. If I'm looking for negative 315 degrees, what quadrant do we think that's going to be in? Okay, why? Why do you think it's going to be in quadrant 1?
Because you're going down or clockwise, and we know that like the 90 degrees is equivalent to 270, and 315 is larger than 270 but less than negative 360.
Yeah, we could almost put our degree measures of the quadrantal angles in there to kind of remind us that we're counting in the negative direction, and then negative 315 is actually exactly halfway between negative 270 and negative 360. So all we're doing is counting in the opposite direction. So we should get to here, except that we counted this way. Okay, and so that is what negative 315 degrees looks like. Okay. Once we've got that, now to find the radian measures, we can actually start in the exact same way that we did for the previous example. Okay. So we've got our theta over 180 equals theta over pi. And this time we're going to plug in negative 315 over 180 equals theta over pi. All right, so a little bit less nice numbers, but again, let's go ahead and try and do a little bit of mental math. What could be a good number to try and reduce the top and bottom by? Yeah, 5 is a great one. So if we divide both the top and bottom by 5, all right, I think we end up with 36 in the denominator. 180 divided by 5 is 36. I think we end up with negative 63 in the numerator. Okay, that one's a little tougher to do mentally, but I like how quickly some of us were able to identify what we should reduce by. That's a really great place to start. Okay. All right, we're going to follow the same process. We're going to go ahead and multiply by pi. So we'll get theta equals negative 63 over 36. And I like to put the pi on the top. Can we reduce this fraction anymore? And what would be another nice number to try dividing by? Yeah, I think 9 actually takes us to where we need to be. Turns out we're going to end up with negative 7 pi over 4. Again, you can put the radians, you cannot put the radians. If you don't write any symbols at all, you're implying that it's radians. Okay. All right, so before we talk about the unit circle measures, I want to do a very quick sort of overview of a shortcut. I don't know how short the shortcut is, but it's something that for me as a very visual learner, it helps me understand how all of these numbers come to be on the unit circle, okay? So I want us to kind of imagine ourselves back in elementary school sometime, okay, before things got, hopefully too complicated. Hopefully they didn't get too complicated. But let's say that I have a candy bar, okay, and this candy bar is cut into 4 equal pieces, all right? So we have 4 pieces that are all the same size, and let's say that you choose to give 1 piece to your friend. What fraction represents the piece you gave to your friend? Yeah, 1/4, right? Okay. Well, let's say that you had the same candy bar, you divided it up into 4 pieces, but you gave 1 piece to your friend and then they were like, can I have another one? That was really good candy bar. And you were like, okay. How much of the candy bar did you give to your friend now?
Half of it.
Yeah, you gave them half. And maybe more precisely, you gave them 2/4, which you then reduced to make 1/2, right? Okay. Well, let's say that you had a candy bar. And this time you were like, you know what? People will be asking me for a lot of pieces of this candy bar. So I'm going to break it into 6 pieces now. And you give 1 piece away to a friend. What fraction of the candy bar did you give to your friend? 1/6. Good. Okay. Same candy bar, same friend is like, hey, can I have another piece? What fraction did you give your friend?
2/6 or 1/3.
Good. 2/6, or we reduce it, we get 1/3. All right. Now I'm writing the unreduced versions for a very particular reason. All right. So this friend, man, at some point, maybe you need to tell them to buy their own candy bar, but they're like, can I have another piece? And you're like, okay. So you give them another piece. How much did you give them? Yeah, 3 out of your 6 pieces, or 1/2, right? Okay. Now let's say that you had a candy bar. Oops, make it the same size as all the other candy bars. All right. And you're like kind of wise to your friend now. You know they're going to ask you for like more and more pieces. So you cut your candy bar like this. And you're like, and they're like, can I have a piece? And you're like, sure, you can have this piece. What fraction of the candy bar did you give them? Yeah, maybe less than 1/6. Let me ask you a different question. Did you give them 1/4 of your candy bar? Okay, why not? How come this is not equal to 1/4? You gave them 1 out of 4 pieces. Okay. So as silly as this little exercise might seem to you, right? Exactly. And I think, Jesus, you say it in a much more grown-up way than the point I've been trying to make. But in all of these previous examples, all of the pieces were divided up equally, right? They were equally distributed or properly distributed. But when I draw a picture like this, the sizes are not the same size. So I can't say that one of the 4 pieces means 1/4, right? That's something that like maybe we learned a long time ago and we kind of forgot about, but when we're thinking about fractions, it's really, we have to be counting the same size pieces. Okay, we have to be counting the same size pieces. Why are we talking about fractions and candy bars? Here's why. So earlier, let's see how well we can draw this. Oh, well, that's okay. So we have a half circle. That's terrible. Okay, let's try this again. Last time, we'll just go with whatever we get here. Okay, it's just going to be that kind of day. So you have a half a circle. Okay, you have a half a circle here. If this is 0 radians, how big is this again in radians? Yeah, it's pi. Okay. So this is the worst diagram ever. Okay, so now we cut this in half. So how big is this angle? Okay. Right, because there's 2 pieces, but they are the same size, right? If Judy could draw a better diagram, then it would be the same size on both sides. Okay. How about if I cut this in half? What's that angle measure? Okay. Let me erase this pi over 2 for a moment. Let's say I cut this into 4 equal pieces, right? We're using the word equal here loosely. This is my attempt at being equal. I am not trying to draw something like the blue diagram, okay? So if I start at 0 and I go to pi, this is pi over 4, okay? How many together is this if you don't reduce? Okay, 2 pi over 4, great. How many is this? Great. How many is this really? Right? So if we imagine just the top half of the unit circle and we cut it into 4 equal pieces, we get 1 pi over 4, 2 pi over 4, 3 pi over 4, and 4 pi over 4. If we can reduce, we reduce, right? Nobody says 4 pi over 4. Everybody says pi. And few people say 2 pi over 4. They usually say pi over 2. Let's try cutting up this half circle. Oh gosh, in a different way. Okay. This time I'm going to cut it into 6 equal pieces. This is 0. How big is this? Oh, that didn't show up on the screen. There we go. How big is that? All right, it is 1/6. Great. Unreduced, what is this? Right? In other words, how many slices do I have? Right? Or how many pieces of chocolate? Yeah, 2 pi over 6. Great. How many slices do we have here? Yep. 3 pi over 6. The next one will be 4 pi over 6, 5 pi over 6, 6 pi over 6. Right? I took something and I cut it into 6 equal pieces. It's not different than the candy bar and you cut it into 6 pieces and you gave 1 piece to your friend. Or you gave 2 pieces to your friend, but you didn't call it 2 over 6, you called it 1 over 3. Right? So we might say this is pi over 3. What name would we give this one? Nobody's going to say 3 pi over 6. We would all say good, pi over 2. All right. I don't think that many people would say 4 pi over 6 though. What might be a better name instead of 4 pi over 6?
One over 3 pi. Well, 1 pi over 3.
Let's think about how what if you gave away 4 of the 6 pieces of chocolate?
Oh, 2 pi over 3.
Yeah, 2 pi over 3, right? So we would call this 2 pi over 3. Great. Does 5 pi over 6 have another name? No, I don't think we can reduce that one. You gave 5 out of your 6 pieces away. That's it. But 6 pi over 6, right, is another name for just pi. Right? So here's the thing. If you know how to do this, which I know you all do, then you also know how to do this. You just have to kind of believe in yourself that you can do it. Okay. I don't want to spend a ton of time writing out the angle measures here. All right. But as I think a exercise for you to do, I would fill in the degree measures again, just to make sure you know how to do that. And then in the boxes that are kind of like rectangles, I would put the radian measures. Okay, so for example, we know this is 0 degrees. It is the same as 0 radian. Right? What's the next nice degree number again? In the positive direction? 30 degrees. Okay. This looks like it's going to be 6 pieces to make up the top half, right? 2, 3, 4, 5, 6. So 30 degrees in radians, we would say is pi over 6. Anyone tell me what 45 degrees is in radians? Yeah, pi over 4. And again, if you think about this, you have 4 equal size pieces in the top half. So 1 pi over 4. (60°). If this is pi over 6, this is 2 pi over 6, right? 2 pi over 6, we reduce, and we get pi over 3. Okay. Now, I am fully aware that there are a bazillion websites out there that will tell you what these angle measures are, what the radian measures are, even what all these coordinates are on the outside. I cannot stress to you enough how important it is, especially if you have access to a printer, print out a bunch of these blank ones and just go through it and just write them out until you know them inside out. Because we're going to be getting into some pretty complicated stuff where the last step is going to be find that value. And if you don't know where it is, that's going to be the thing that throws your whole problem. That's kind of sad, right? You're like setting yourself up to not be successful if you don't know this really, really well. Okay, so I am saying this not to scare you, but to be very real with you that if you learn this, oh man, this course is going to be significantly more straightforward for you. Okay. All right, got a little bit left to finish up, and here is where we're going to go. All right. So I want to talk a little bit about some vocabulary. All right. So we have some coterminal and reference angles. All right. So coterminal angles are 2 angles in standard position that have the same terminal side. Okay. So here's what I mean by that. Let's say we have a grid and we have our initial side and we have our, our terminal side. All right. This and this, so the light blue and the dark blue both represent angles. They are coterminal to each other because they have the same terminal side, meaning they start at the pink and they both end at the purple. All right, so coterminal angles are 2 angles in standard position that have the same terminal side. All right, so what's a reference angle? An angle's reference angle is the smallest acute angle formed by the terminal side and the horizontal axis. In this picture, is the light blue one the reference angle or the dark blue one? Yeah, exactly. All right. This is our reference angle. So when we say reference angle, it has to be bigger than, it has to be smaller than 90 degrees. Has to be. All right. These are not the only 2 angles though that we could create that have the same, that are coterminal. Okay, so something that is, we will see is sometimes someone might draw an angle like this. Okay, the initial side is here the terminal side is here. So wherever that angle ends, that's the terminal side. Okay. The reference angle for this is right here. This angle, I went around 1 time, 2 times, and a little bit. But the reference angle is just the little bit, right? That acute angle. Why is this important? Sometimes we get angles that are bigger than 360 degrees, and we need to find out what their actual name is. Like what is the most convenient name we can call this angle, okay? The other side is called the coterminal angle. No, the angles themselves are coterminal. So like the dark blue and the light blue are coterminal to each other. This side where they end, that's the terminal side. I know that's confusing. Okay, cool. All right, so let's look at some angles that have not so nice names and figure out what the name would be better called, okay? So I clicked a little how-to from your textbook, all right? So some of you asked about that textbook. I try and use resources from there. That way, when you go back and read your textbook, you can kind of see like, okay, they do give me some steps. Maybe this is helpful, all right? So given an angle greater than 360, what are we gonna do? We're gonna subtract 360 from the given angle. If the result is still greater than 360, you keep subtracting again until you get a result between 360 and 0. Your end result is an angle that is coterminal with the original angle. All right. So here's what we're doing when we subtract. We're saying like we started here. If I subtract 360, I'm going to get to here, right? If I subtract 360 again, that's like going around the circle another time. So by subtracting 360, we can get to the acute angle or our reference angle. Okay. So let's try this with 900. We've got 900 degrees. Let's subtract 360 and we get 540. What do we do now? Great, we subtract 360 again, right? So 540 minus 360. And I believe that gives us 180. What do we do now? That's it. Okay, how did we know that we were done? How did we know we didn't need to subtract again? Yeah, 180 is between 0 and 360, right? So let's just sort of unpack what this means though. This means that 900 degrees is coterminal to 180 degrees. All right. My question to you is how many extra times did I go around the circle from 180? Yeah. Okay. We subtracted 360 once, we subtracted 360 again. That means we went 2 extra times around. Right? So we could call it 900 degrees, but that's really overkill because it's the same as 180 degrees. Okay. All right. What do you think we should do for this? I have negative 200 degrees. Why do you say plus 360? That's not what the directions say. The directions say subtract 360.
I'm thinking plus because we're basically going in the reverse direction whenever it's a positive number. And in this situation, it would be plus if we're going from negative 200.
Okay. And Jesus, what do you mean by saying keep it the same? Like, should we keep at like subtracting 360? What do you mean?
No, just leave it at negative 200 degrees because it's under the 360 degrees.
Is negative 200 between 0 and 360?
Okay, never mind. I said it
Right?
wrong.
Okay.
Yeah.
So yeah, that's actually a really good thought because does the negative sign matter? And it turns out it does matter, right? If we had 200, you would be absolutely correct. We could keep it the same. But we got negative 200. We have to figure out how to get rid of that. And so if you read the directions and you were like, oh, just try the same steps, maybe you would say, okay, well, let me subtract 360, see what happens. You get negative 560. And then you're like, I don't know, let me try it one more time. And you keep subtracting, you get negative 920. Do you think that if you keep subtracting, you'll end up with a number between 0 and 360? And I hope that our answers would be no, right? In fact, our numbers are getting more and more negative. So we want to get to a number between 0 and 360, right? And so I think Dallas's intuition is actually pretty good. If I want to get to a positive number, what if we add 360? If we add 360, we end up with 160 degrees. Is that a number between 0 and 360? And I think we'll all agree that is a number between 0 and 360. So we found out that, let me write this in blue, negative 200 degrees is coterminal to 160 degrees. Okay. All right. So part of this is about the decision making, right? You might get a rule, and if you use that rule every single time, it's probably going to break down at some point. You're probably going to encounter situations where you can't use that rule. And so it's really useful for us to think about how do we modify the rule, right? So we started with a positive angle. We thought about how we could change it if it's a negative angle. What do we do if we have something in radians? We got 11 pi over 3. What do we think we should do with this 11 pi over 3? Right? This would be weird. Weird for a lot of reasons, but probably weird because we have radians and degrees and we're mixing them, right? So yes, we could change it to degrees. However, I want us to know how to work comfortably with radians. In fact, we're not even going to see degrees for like a big part of this course. Okay. We are going to be working with all these fractions. And so I really want us to just jump right in and be comfortable with it, or at least pretend that we're comfortable until we really are. Okay. So I think instead of changing this to degrees, we could change the 360 to radians. So instead of minus 360, we can do minus 2 pi. That's the same as 360, right? But how do I subtract these? So I don't think I can subtract them the way that they're written.
You want to times the 2 pi by 3/3.
Yeah, so we'll get 11 pi over 3 minus 6 pi over 3, right? So we get a common denominator there. Great. We subtract them, we get 5 pi over 3. Are we done? Do we need to subtract again?
Yeah, we're done.
How do we know we're done? I would agree.
Because 5/3 is 1.6 kind of. And that's less than 2. So should be good below 2 pi.
Mhm. So if the number is between 0 and 2 pi, right? 0 and 2 pi is the same as saying between 0 and 360. So if it's between those two, we're good to go. All right. And it is. 5 pi over 3 is between 0 and 2 pi. So we are done. And we only went around the unit circle one extra time here because we only subtracted 2 pi one time. Okay. For the sake of time, I'm going to suggest that you do example 5 on your own. I think it'll be good practice to think about fractions, adding, subtracting, thinking about that strategy. Okay, so please try this one on your own. And if you're like, I kind of want to go to office hours, but I don't know what to ask, you can do this problem, come to office hours on Wednesday and say, hey, I tried doing this problem. Can you like look it over for me? Can we make sure that it's correct? Absolutely. Okay. I don't know what you mean by simplify, because it could be that if you had like you could get to a point where it's like (13 pi over 6. You can't reduce that anymore, but that's not less than 2 pi. Right? So you got to be really careful about that. Okay. You do want to get to a point that it is between 0 and 2 pi. All right. So one of the other things that I try to do during class is think about like study strategies, right? Because I know I'm asking you to memorize a lot. I know I'm asking you to learn a lot in a very short period of time. And so as an exercise in the privacy of your own learning environment, thinking about this how-to from your textbook, they told you how to do it for degrees, but only positive angles, right? If you want to write your own rules for like what it means to have a negative degree, or your own rules for what it means to have a positive radians or a negative radians, I would encourage you to kind of use this space so that you can write down your own rules that we've done for 3, 4, and 5. Okay. I think that one of the things, and I'll talk about this next time, is we have a reference sheet that you're able to use on exams, but a reference sheet, if all you write is the formulas, but you don't know how to use them, might not be really valuable to you, right? So maybe thinking about this as a way to make those reference sheets even better, or sometimes just as a study technique, right? If I know one case and I know how to get to the other cases, then I now know more than I did before when I thought they were all separate cases, right? So again, sort of an exercise for you to think about studying and retaining information, because we are going to use all of this information like all semester long, okay? All right, so our last piece for today, we're taking a look at length of an arc and area of a sector, all right? So it boils down to this. If we have the angle in a circle, we can find two things, all right? We can find the length of an arc, which is like this part here, or we can find the area of a sector, which is like this whole purpley sort of area here, okay? I like food a lot, so I tend to use a lot of food examples. My apologies if that makes you hungry during this class, but hopefully you have snacks that are accessible. All right, so if we think about the length of an arc, that is this part right here. And I tend to think about that like the pizza crust. Okay, so not like the cheese and the toppings part, but literally just the edge, like the crust part, okay? And so it turns out that we have a formula that will help us find the arc length, all right? And so we use the letter S here. I know the word arc length doesn't have an S in it, the formula, and we call it an S, just go with it. But the arc length is equal to the radius of your circle times your angle, okay? But here's the catch, and you need to be really careful about this. R stands for the radius. That's all fine and good, right? R stands for radius. Theta is an angle, but it's an angle in, whoa, in radians. Theta, radians, right? So if you want to use this formula, your angle better be in radians. Okay, so you have to know how to convert, like we talked about earlier, so that if you have an angle in degrees, you can convert it so that you can use this formula. Okay. On the flip side, we have the area of a sector, all right? That's probably the part of the pizza that I like better, which is the part with the cheese and the toppings, whatever toppings I want, right? So this region right, this area is called a sector. And the formula here, right, we have area equals 1/2 theta times r squared. And again, r equals the radius. That's all fine and good, but theta is the angle in radians, and we'll write that in all capitals. It is the angle in radians. Okay, so we really need to make sure we know how to work with things that have pi in them and work with them comfortably, because the formulas kind of force our hand to be that way. All right. All right, so let's finish up this lesson with 2 examples. We're going to do one where we find an arc length, one where we find the area of a sector. You can tell that I haven't lectured in quite a bit because I feel like I'm already losing my voice, and you know, we're only on the first day, but here we are. So example 6, find the arc length of a circle with a diameter of 8 meters subtended by a central angle of 220 degrees. All right, so arc length, we're thinking, okay, arc length of a circle. The formula for arc length is S equals R theta, right? Now, even though this word problem only takes up one line, I haven't given you anything that you can use right off the bat. You have to do some work to find R and to find theta. Okay, so let's do that work together. How do I find the radius?
Divide the diameter by 2.
Perfect. One of the most classic twists in a problem, right? You're working through a problem, you're like, okay, I just plug in the 8 as the radius, blah, blah, blah. But we want to make sure we take the time to recognize that radius is 8/2 or 4 meters, right? We want to make sure we do that work. And we could put that 4 in for the radius. This central angle of 220 degrees, same thing. I can't just take 220 degrees and put that into the formula, right? Because I have to have an angle measure in radian. All right. What's that formula we talked about earlier? How do we convert between radians and degrees?
It's degrees over 180 equals theta degrees over pi.
I'll take theta over pi. Yeah, where do we plug in the 220? Top
The
right or top
degrees,
left?
top left.
Yeah, top left. All right, so we're gonna get 220 degrees over 180 degrees equals theta over pi. Great. I bet this group is gonna tell me, get rid of those zeros, right? We have 22 over 18 equals theta over pi. Can we continue to reduce? I think we can. Yep, what can we reduce by? Yeah, we'll cut everything. 22 divided by 2 is 11. 18 divided by 2 is 9. Great. Now we can multiply that pi over. We'll get 11 pi over 9. And that is what goes in for the angle. All right. So we have our radius that we want to be really thoughtful. We're using the radius and not the diameter. And we have our angle, and it is in fact in radians, not in degrees. Right? Once we have that, we end up with 44 pi over 9. And if I'm talking about arc length, what units do you think we should put at the end of this? So radians would be like, how big is the pointy part of the pizza, right? But that's not what we're measuring here. We're actually measuring like how long this piece is. Yeah, meters is definitely where we want to go. Okay, so because we're looking at length, because we're looking at the length of something, we want to use whatever units talk about the length. All right, so our arc length is 44 pi over 9 meters. And please leave things in exact form. Do not turn that into a decimal. We're beyond that point in our careers. If we have a fraction, it's probably best to just leave it like that. And we want to be super careful. Did we put all our units where we wanted them to go? Okay. All right. Last problem of the day, we'll take a look at an area of a sector. All right, so again, that's like the good stuff in the pizza, like the cheese and well, I mean, if you're lactose intolerant, maybe that's not your favorite part, but like, I really like the inside of part of the pizza, right? So like now we're saying like, how big is that part of the pizza, right? Again, we've got a central angle of 60 degrees and we've got a radius of 5 centimeters. And so the first thing that I like to do is write down the formula. All right, before I do anything else, I like to write down the formula so I know where I'm going. And that's something I've seen a lot of you folks do, is start with the formula and then plug in what you need to plug in. I think that's been really good for sort of catching your own mistakes as you go. All right. All right, so I've got a radius of 5 centimeters. I can actually put that right in for the R, right? This was not that sort of real slick trick where I was like, hey, here's the diameter. I hope you put this number in and I hope you don't divide by 2, right? This is like, all right, I'm going to give you the radius. Here we have the radius. However, I hope that we don't go and put 60 degrees in for our theta, right? We need to convert this to radians before we can do anything. So if we think about our formula from above, I'm going to put that 60 in the top left. All right. Reduce that fraction for me. What do we get?
1/3.
1/3, excellent. 1/3 equals theta over pi. So theta is pi over 3. Now I have the value I can plug in. So I get 1/2 times pi over 3 times 5 squared. And so what does that get us? 25 pi over 6. Units for this. Looking for area. Right, I'm looking for area. I'm not looking for length. So yeah, precisely. It's not going to be centimeters, but it is going to be centimeters squared. Okay. So not too bad with these last 2 problems, mostly just plugging things into the equation, but being really careful. Do I have the right information or do I have to do a little bit of work to make it the right information? Okay. All right, so my friends, that is it for today. All right, I know we've kind of talked about a lot of different things, but if you take a look at quiz 1, that is your first assignment. Well, after that, there was the interview, the partner interview, but your quiz number 1 is due on Wednesday by 11:59 p.m. Okay. There should be all sorts of information in the syllabus about what that means, where to find the assignments, how to turn them in. But if you have any questions, please ask before the first deadline, not like after the first deadline, okay? This is an accelerated course, so I want to make sure that we're all starting off with like 25 out of 25 on that quiz so we can feel like, all right, I'm walking into this first week, A+ all the way, I got this, right? So as many points as we can kind of get in the beginning is definitely really helpful. I think it keeps us from getting really stressed later on, but also knowing that we're going to use this information throughout the entire course. If you know the stuff at the beginning, you're going to be able to use it as we learn all that new stuff as well. Okay, so in a lot of ways, not just grade wise, but like that understanding piece, I want to set us up to be really successful. Okay. So let's stop this recording.